current unit of study is going to be on buffer systems. A buffer system is some type of chemical system that can resist a change in pH upon addition of either an acid or a base, is what defines something as a buffer system. If we examine a couple titration curves, we can identify an area where buffer systems are present. In this weak acid, strong base titration, at the beginning there's only weak acid HX. At the equivalent point there's only salt X minus. But in this area, where the pH is staying fairly constant, even though we're adding sodium hydroxide, we'd have some kind of mix of weak acid and X minus. Reason being, as we add sodium hydroxide, the acid's getting neutralized, so the amount of acid is going down. Meanwhile, the amount of X minus or salt is increasing. Eventually, when we get to the equivalence point, exclusively there's only salt present, just as at the beginning there's only acid. But in this area, which is the buffering region, we have a mixture of weak acid and salt. Similarly, in a weak base, strong acid titration, we find a buffering region right in here, where once again, say we had something like ammonia might be a weak base, we'd have our salt, ammonium chloride, at the equivalence point. But in this area, there's going to be a mixture of the weak base, ammonia, and the salt, which would be the ammonium ions. So once again, to make a buffer, we have to have that mixture of either weak acid, in this case, and salt of weak acid, or in this area, weak base and salt of weak base. So let's say we have a buffer that's a mixture where we have some weak acid and we also have some salt present. That'll place us somewhere in this region on our titration curve where we have this mixture. Here's how a buffer system works. If we add hydroxide ions, hydroxides are going to bump into the hydroniums, and that's going to turn into water and water. Because the hydronium concentration went down, this reaction is going to shift to the right. By shifting to the right, the amount of X minus goes up, the amount of HX goes down, and we'd move slightly to the right in this titration curve. The H3O plus ions that got taken away by the OH ions get replaced, and that allows the pH to remain relatively constant. On the flip side, if we toss in some acid, that adds additional hydronium ions. The hydronium concentration goes up. That's going to cause this equilibrium reaction to shift to the left. The amount of HX would increase, the amount of X minus would go down, and what we have is, by shifting to the left, the amount of hydronium ends up remaining fairly constant. This would cause a slight movement to our left on the titration curve in our buffering region when we add HCl. Once again, though, the key being that because the hydronium concentration remains relatively constant after our shift, the pH remains relatively unchanged even though we added some acid to the solution. A key feature for a buffer system is a buffer has to be some kind of equilibrium system that allows the reaction to shift right or left in response to addition of either base or acid. Something such as this, which is a strong acid with some salt, cannot shift backwards, which makes this a system that cannot provide buffering. To buffer, we need an equilibrium system. Here's some examples to see if they make a buffer. Let's examine this first one. We have 1 mole of HF and 1 mole of sodium fluoride. That's a mix of 1:1 of weak acid and salt. That would place us right here on our titration curve, which is well within our buffering region. This is something that would create a buffer. If we look at our next one, we have 100 milliliters of 0.1 molar acetic acid, which would be right here, and we have 50 milliliters of sodium hydroxide. That's sufficient sodium hydroxide to neutralize half of the acid, which would move us along our titration curve right to this point. We now have a mix where it's a 1:1 ratio of acid and weak acid salt. So since we end up right here with this mixture, that is something that does create a buffer system. Looking at a couple other examples, here's one. We have 1 mole of potassium iodide, which is a salt, and 1 mole of potassium chloride. All we have here is a mixture of a salt with a salt. That will not create a buffer system. If we look at this one right here, we have 0.25 moles of nitric acid and 0.25 moles of KOH. That's sufficient base to neutralize all of the acid, and it's a strong acid as well. All that's remaining here is we have salt and water. A mixture of salt and water is insufficient to create a buffer system. So look at this one. We have 1 mole of ammonia. Ammonia would be right here on our curve, and we're adding half a mole of HCl. That's going to move us along the curve, neutralizing half of the ammonia, bringing us right to this point. That's in our buffering region, so this is something that would create a buffer system. The key being, to make any buffer system, we have to end up with some kind of mixture that'll put us in this region or on our weak base curve in this region, where we have that mixture of weak acid and salt of weak acid, or here where we have weak base and the salt of that weak base. With those mixtures, we end up with a buffer system. Let's do a quick calculation. This is one where we're given a mixture of weak acid and salt. We want to know what's the pH of this buffer. What we're given in the problem, we have 0.4 moles of nitrous acid in 1 liter of solution, so we know our nitrous acid is 0.40 molar. We also know that we have 0.6 moles of potassium nitrite also in 1 liter of solution. So our initial concentration of potassium nitrite is 0.60 molar. Initially, we'll say there's 0 amount of hydronium. Because the hydronium is 0, this has to be a plus. We don't know how much our change is, so we'll call it X. Because we have a 1 to 1 to 1 ratio, this goes up by X, and the nitrous acid will go down by X as the system reaches equilibrium. At our equilibrium line, the size of our X here compared to 0.40 or 0.60 will be very tiny, so we can eliminate that X value. We can set up our Ka expression. We can substitute in our values for our salt and for our acid, and when we solve for X, that'll give us the hydronium concentration. Our hydronium concentration comes out to be 3 times 10 to the negative 5th molar, giving us a pH for this buffer system of 3.52. Another common type of buffer question is seeing what do you need to do to get a buffer that has a specific desired pH. Now in this case, we want to make a buffer with a pH of 4.2. The pH will let us figure out what our H3O plus concentration is in this buffer system. Using our pH, we can solve for the desired H3O plus concentration for this buffer system. We now know what H3O plus concentration is required to give us our pH of 4.2. In the Rice strategy, we can put in our H3O plus concentration for the equilibrium value that we just got from our pH. The problem's asking us to find what ratio of sodium acetate to acetic acid do we need to give us this desired pH. A suggested strategy is make the acetic acid value 1.0, make the amount of sodium acetate X. So we'll solve for X, make the acetic acid 1.0. Setting up our Ka expression, we have the amount of salt that we're going to need, or acetate, as X. We'll represent the acetic acid as 1.0, and we know our hydronium concentration from the pH. When we solve for X, that'll give us how much salt we need compared to the amount of acid to create a buffer with a pH of 4.2. Solving for X, we get a value of 0.28. What this tells us is to make this buffer, we need a salt to acid ratio of 0.28 to 1.0. As long as we mix our salt and acid together in these proportions, we'll end up with a pH 4.2 buffer using this system. This next problem takes a look at determining the pH of something in a buffer solution after we've added, say, HCl or NaOH. We still use the equilibrium for the weak acid with water in our Rice strategy. Now, one thing we can do for buffers, because we have a mixture of salt and weak acid, and this is buffers, this works for buffers only, is we can do the equilibrium problem in terms of moles. So what we can do in this problem is we have a 100 milliliter sample of our buffer solution. Now originally the buffer was 1 liter, so we're using 1/10 of the moles. So we have 0.05 moles. 0.05 moles initially of acid and 0.05 moles of salt present. H3O plus we can just say is 0. Now this problem indicates we're adding hydrochloric acid, which is the same as causing the hydronium concentration to increase. What that'll do is drive the reaction to the left, so we know that the amount of acid is going to be a plus, the amount of salt in our change is going to be a minus. The size of the change is determined by the moles of HCl that we've added. Using a proportion, we can find how many moles of acid are present in our 10 milliliter sample. It's 0.01 moles of HCl. This gives us the size of our change. So the salt is going to go down by 0.01. Our acid is going to go up by 0.01 moles. We have our equilibrium value now of acid is 0.06 moles. Salt has changed to 0.04. The H3O plus is going to be X, whatever the value needs to be once the system reestablishes equilibrium. We can set up our Ka expression, solve for X, which is our H3O plus concentration. Our H3O plus comes out to be 2.7 times 10 to the fifth molar. And our pH after the addition of the hydrochloric acid is now a pH of 4.57. The next problem is the same type of thing, except we add base to the system. We start out again with 0.05 moles of acid. We have 0.05 moles of salt. By adding base, that's going to cause the hydronium concentration to drop. When the hydronium concentration drops, the reaction is going to shift to the right in response to that change. So our acid change is going to be a negative. The amount of salt is going to be a positive. The size of the change is based on how many moles are present in our base sample that we've added. Using a proportion, we can find out we have 0.010 moles of sodium hydroxide being added to the system. That gives us the size of our change. The acid's going to go down by 0.01. The salt's going to go up by 0.01 as the reaction shifts to the right in response to the base. So our acid will be 0.06 moles at equilibrium. The acid will be 0.04 moles. The salt becomes 0.06. The H3O plus becomes X, whatever it needs to be once the system re-equilibrates after the equilibrium shift. We can set up and use our Ka expression to solve for the H3O plus concentration. After the system is re-equilibrated, the H3O plus comes out to be 1.2 times 10 to the negative fifth molar, giving the system a pH of 4.92 after the addition of the base.